Welcome back, everyone. So in this video, we're going to go through the three main types of conservation of momentum problems. I'm going to kind of lump elastic and just regular inelastic collisions together. The reason being the math for conservation of energy problems for those two are pretty much the same. You'd have to then go through and calculate the kinetic energy before and after to see if it's conserved to determine if it's elastic or inelastic. I'm not going to do that here today. I'm just going to focus on the conservation of momentum. All right, so to start, let's say we've got two carts. Okay, the one cart is 15 kilograms and is moving to the right at 22 meters per second. It's on the same kind of path as a 34 kilogram cart that's also moving to the right, but this one's moving at 8 meters per second. Okay, so this is before anything happens. 15 kilograms moving to the right at 22 meters per second, 34 kilograms moving to the right at 8 meters per second. All right, cool. Now, obviously, since that 15 kilogram cart is moving faster, it's going to eventually collide with the 34 kilogram cart. So, after they collide, right, they're going to bounce apart. And what I want you to know, or I want you to figure out, is how fast and in which direction, so the velocity of the 15 kilogram cart, if the 34 kilogram cart moves to the right at 13.5 meters per second after the collision. All right, so what is the velocity of this cart after the collision? All right. So let's set up our equation, okay? To do this, we first have to look at how many objects there are before and after the collision. We need as many momentum terms as there are objects. So before the collision, there were two objects, the 15 kilogram cart and the 34 kilogram cart, all right? So when setting up our equation for before the collision, we need an mv, momentum term, for each thing. So I'm going to write that down as m1 v1 plus m2 v2. All right. Now, after the collision, there were still two objects. So I'm going to have a momentum term for each object after the collision. So that's m1 v1 prime plus m2 v2 prime. All right. So that's how I basically set that up. Now, if you're used to saying a prime as being a derivative from a calculus class, from that notation of a derivative, that's not what's happening here. I'm not taking the derivative of the velocity. All I'm doing with the prime is making a notation so I can keep track in my head that these speeds are different than these speeds. That's all I'm doing. If you have another way that you'd like to make sure you keep track, be my guest. But this is just how I've always done it, so this is how I do it. Anywho, let's plug in some values. All right, let's set our m1 to be our 15 kilogram object, with v1 being our 22 meters per second, plus m2 is 34 kilograms, moving at an initial 8 meters per second, equals 15 kilograms times an unknown v1 prime, plus 34 kilograms, moving at 13.5 meters per second after the collision. I kind of ran out of space, so I just scooted it down there. Now, keep something in mind here. 15 kilograms times 22 meters per second. 34 kilograms times 8 meters per second. Unknown velocity, 34 kilograms times 13.5 meters per second. I kept all of these positive. They're all traveling to the right. This cart started traveling to the right. This cart started traveling to the right. After the collision, the 34 kilogram cart still traveled to the right. I kept them all positive. Any objects going in the same direction must have the same sign. All right? And that's how we're also going to be able to determine the direction of our v1 prime here. All right, so let's do some calculations. Well, we have 15 times 22, which is 330 kilogram meters per second. okay, plus 34 times 8 is 272 kilogram meters per second, okay, equals 15 kilograms times V1 plus 459 kilogram meters per second. Sorry, I'm kind of running out of space here, so it looks a little sloppy. All right, well, now I can rewrite this. 330 plus 272 is 602 kilogram meters per second equals 15 kilograms times your unknown V plus 459 kilogram meters per second. And just for space purposes, right, you'll do the math, right? So you have 602 minus 459, then all divided by 15, and you end up with a final speed of 9.53 meters per second. 9.53 meters per second. All right? Notice that it's positive, which means that it is also still moving to the right. That 15 kilogram cart did not get knocked backwards. Okay? Excellent. So that is a basic problem for an elastic or an inelastic collision. Hooray! Now, again, if you want to tell the difference, just go through, find the kinetic energies before and after. Same basic process. You can use the kinetic energy equation. See if they're equal on both sides. If they're not, kinetic energy was not conserved. It is inelastic. So you can do that on your own. All right. Now, the next scenario we have here is, again, two carts. Okay. Cart 1 is 22 kilograms, moving to the right at 12 meters per second. And we have a second cart of 9.5 kilograms moving in some direction at some velocity. We don't know. That's what we're going to solve for. After the collision, the two carts collide. Okay, they collide, and they're going to move to the right with a speed of 2.25 meters per second. Okay? So, what I want to figure out now is whether or not, not whether or not anything, I want to figure out the velocity, magnitude of the velocity, and its direction of this cart. Two objects before the collision, I need two momentum terms. m1v1 plus m2v2. One object after the collision, I need one momentum term, right? Even though there were two objects, they collided, they moved together as one thing. mv. Okay, so here's my basic setup. My momentum terms for my original two objects, my momentum term for the object after. All right, m1, 22 kilograms, times v1, we're going to set to the right as positive again, 12 meters per second, plus 9.5 kilograms times an unknown v, all right, equals, okay, well, our mass here is going to be the combined mass of the two objects. So 22 plus 9.5 is 31.5 kilograms times the velocity of that particular object, which we said was 2.25 meters per second. All right. So let's do our calculations. 22 times 12 is 264 kilogram meters per second plus 9.5 kilograms times V equals 70.875 kilogram meters per second. All right, now let's rearrange. Okay, I want to solve for my V. So what I'm going to do is I'm going to subtract my 264 from both sides, so I can leave this by itself. Right? So I'll end up with 9.5 kilograms times V equals 70.875 kilogram meters per second minus 264 kilogram meters per second. Check this out. You'll notice now I'm going to have a negative sign, right? Because 70 minus 70 point blah, 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 minus 264 is going to yield a negative sign. What does that negative sign mean? Well, if we set to the right to be positive, a negative sign would mean to the left. So we know our direction now, it's to the left. Okay, so let's do our calculation. I ran out of space, so I can't do the whole thing. So 70.875 minus 264, all divided by 9.5, and we find our speed to be 20.34 meters per second. My apologies, negative 20.34 meters per second. Again, it's moving to the left. Okay, so originally those cars were heading toward each other. They collided, and the 22 kilogram cart sort of overtook the 9.5 kilogram cart. Excellent, 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 excellent. All right. So, our last scenario. I'm going to draw, similar to what you may have seen in the other picture, a triangle piece and a square piece. So we have this object right here. It has a total mass of 88 kilograms. And we're going to say it's going to move to the right. It's going to move to the right with a speed of 4 meters per second. Okay, so it's one thing originally. Afterwards, it's going to split into a triangle piece and a square piece. The square piece is 66 kilograms, and it's moving to the right with a speed of 12 meters per second. Okay. The last piece, obviously, will have a mass of 22 kilograms, and I want to know the velocity of this object. What direction is it going? How fast is it going? Now, you might think, oh, well, it's going to the left. Doesn't necessarily have to do that, right? It can still continue to the right a little bit. We have to do the calculation to figure it out. We can't just assume, all right? You can always throw in, if they don't give you any real numbers, you can always throw in some fake numbers just to help you along. All right, so one object before the collision, so we need one momentum term for that. Two objects after the collision, so we'll need two momentum terms for that. So that's going to look like m times v for the one object equals m1v1 plus m2v2. All right, let's plug in our values. Okay, the whole mass was 88 kilograms. The speed was 4 meters per second. Okay, we're going to set to the right as positive. M1, we'll say that's the 66 kilogram object. We said that was also going to be moving to the right, but this time at 12 meters per second. Plus our 22 kilogram object times its unknown velocity. All right, let's do some multiplication here. 88 times 4 is going to be 352 kilogram meters per second equals 66 times 12 is 792 kilogram meters per second plus 22 kilograms times your unknown v. All right, to solve for our v, I'm going to subtract 792 from both sides. So I'll have 22 kilograms times v equals 352 kgm over s minus 792 kgm over s. All right, again, I'm running out of space, so I'm just going to say, to solve, do this subtraction, divide by 22 kilograms, and we find, since 352 minus 792 is a negative value, that that object is moving to the left with a speed of 20 meters per second. So you could write that as 20 meters per second to the left, or just negative 20 meters per second. That negative sign represents the opposite direction. All right, so those are just one practice problem for those three different types of scenarios. Well, I guess four if you count the elastic/inelastic type scenario. And that is kind of the most important ways to look at these types of problems. All right, so I hope that helped, and I'll see you next time.